So this video is going to be on the natural numbers, and it's going to be within my playlist on set theory, and it's going to build on the ideas that were introduced in one of the previous videos in this playlist, namely the video entitled Zermelo set theory. Now in that video we introduce axiomatic set theory, we explain why it's necessary, and then we build it from the bottom up. We start by saying the empty set is allowed as a set, and then we look at several of the Zermelo axioms that then allow you to build other things that are going to be allowed as sets within this theory. And we actually, in that video, get to the set of natural numbers. We use the Zermelo construction and we see the axiom of infinity that axiomatizes that this first infinite set, the simplest of the infinite sets, the countably infinite set, is allowed in our new theory as a set. And so we're going to build on the concepts that were discussed in that video in this video. So ideally you would have watched that video before watching this video. However, if you think you're familiar with what I've just been discussing, then you can continue to watch this video and hopefully you'll be able to follow it. In this video we're going to look again at the Zermelo construction of the natural numbers, and we're also going to look at something called the von Neumann construction of the natural numbers. We're going to understand how they're equivalent to one another as far as the set that you overall end up with is concerned, that they both yield a countably infinite set that, as far as set theory is concerned, is isomorphic to one another, just different constructions. We're then going to look at equipping our set of natural numbers with further properties. So we're going to look at equipping it with order properties to make an ordered set, and indeed that's the main advantage of the von Neumann construction over the Zermelo construction, that it's really simple to define an ordering on the natural numbers using the von Neumann construction, whereas it's much more difficult to do that with the Zermelo construction. And then we're going to define arithmetic on the natural numbers. So we're going to put both the addition law and the multiplication law onto the natural numbers, which then makes it a semi-ring. Finally, we'll end the video by discussing the axiom of induction, which is actually a deep axiom of logic. It's the axiom that allows you to use proof by induction as a argument, as a proof, as a form of reasoning. It's the axiom that says that that's okay, that that is a valid logical argument. And we will have a look at this quite deeply. We'll have a look at why it doesn't just follow immediately from predicate logic, because when you initially see it, you wonder, is this really necessary as a separate axiom of logic? Can't this be derived from the other rules of inference, the other axioms of logic? Well, it feels as though it can, but it can't. There is a tiny important bit, subtle important bit, that means that this is necessary as a separate axiom of thought, a separate axiom of logic, and we'll explore that. So we'll have a bit of predicate logic, classical logic at the end of the video. So we really are going to have an interesting video, lots of very deep stuff here. So firstly, just a quick reminder of some of the key points from the video on Zermelo set theory. So remember, all of these things that I've written here, these were all constructible and allowed as sets inside the Zermelo set theory. That followed from the pairing axiom. What you can then do is you can put them all inside a set themselves, like so, using the pairing and the union axiom. So this structure that we've got here is also a valid set inside Zermelo set theory. Because this is hideous, what we can now do is rename these elements. So classically we rename this one 0, we rename this one 1, we rename this one 2, we rename this one 3. So we're just changing the symbols. We're coming up with nicer symbols to represent these things that we know are allowed as elements inside our new theory. And then we get this thing here. So we've now got a nice simple set containing 4 things. And we could have done this differently. We could have just taken these two and had them inside a set and renamed them 0 and 1, and we then have had a set containing 2 things. We could have done these 3 and had a set containing 3 things. We could have made more. We could have had the next one along and the next one along to make sets containing 5 things and 6 things. So why am I bringing this up? What I am trying to illustrate to you is that finite sets are all absolutely fine inside Zermelo-Fraenkel set theory. They're all valid sets, because any finite set you have, you can think of the elements, whatever symbols they may be, and this could have been alpha, beta, gamma, delta, any symbols. Whatever symbols they may be, you can think of them just as relabelings of these things, and therefore it's allowed as a set inside this theory. So any finite set you can think of is going to be allowed as a set inside the Zermelo-Fraenkel theory, which is a jolly good thing because there was no problem with finite set theory in the first place. Naive finite set theory was absolutely fine. The problem with naive set theory, which led to the necessity of axiomatic set theory, was when infinite sets, it was a problem in infinite set theory. You know, Russell's paradox was the massive problem that led to axiomatic set theory, and that is a very much so a problem of infinite sets, not finite sets. So finite set theory is beautiful, finite set theory is fine, and finite set theory is completely taken forth into axiomatic set theory. So that's my first point, that all of these finite sets, no matter what the symbols for the elements are, they're all absolutely valid in axiomatic set theory. So finite sets are allowed. The next step up is to start allowing some of the infinite sets. And the first one you're going to go to is the simplest of the infinite sets, which is the countably infinite set, which is the natural numbers. So this is axiomatized to be allowed as a set in the Zermelo-Fraenkel theory, and that axiom is called the Axiom of Infinity. And a very important concept when we're talking about natural numbers and constructions of natural numbers, and indeed this is going to become incredibly important when we're trying to define addition and multiplication later on, which is why I'm bringing it up as something that's very important, although at the moment you might think surely you could have described this without talking about this, and I could have, but later on it's going to be really helpful to think of things in terms of this, so I'm going to introduce it now. Is the concept of successor rule. So this is the rule for getting the next one along. So from here, the successor of that one was this one. You stuck this one inside a set, and then that was the next one along. This one's successor is then this one. The way you get to it is you stick it inside a set of set brackets, and you've got this one, and then so on. So when we construct natural numbers, and indeed when we try to define further things on natural numbers, it's really helpful to think of successors, the next thing along. It's a very natural concept. That's indeed the concept that led to the whole of the natural numbers. So in the Zermelo construction of the natural numbers, the successor rule, the way you get the next one along is very simple. You take the current thing, so S of k just means the successor of k, it's going to be equal to, you take the current thing and then you put it inside another pair of set brackets, and that's the next thing along, and you can continue on. And in order for something to meet the criteria to be a successor rule that could lead to a construction of the natural numbers, it needs to be the case that the new thing that you get isn't equal to any of the things that you've already had. So for instance, the successor of this one is going to be here in our succession, in our sequence, and it's not going to equal any of these four things that you've already had, and then the next one along, it's not going to equal any of these ones that you've already had. It's going to be something new. So this successor rule has to produce something new, and it goes on and on indefinitely. So for the Zermelo construction of the natural numbers, this is the successor rule. And the Axiom of Infinity says that there is a set which starts with this and then contains every successor. So if it contains an element, it has to then have its successor. So because it contains the first element, it then has to have the successor of it, so it has to have this one, and then because it contains this one, it has to have this one's successor, so it has to have this one, and so on. So it has to contain all of them. That's what the Axiom of Infinity is saying. It says that there is a set that is allowed within the theory that contains all of these things, that contains the initial thing, and then obeys the property that if an element is inside this set, then its successor has to be there as well. So this would be hideous if I continued using the notation here, so I've gone over to relabeling things with the classical symbols for the natural numbers. Again, all I'm doing is relabeling, just changing the symbols. No black magic is happening. So this set 0, 1, 2, 3, etc. on and on forever, all of the successors. So 3 is the successor of 2, 4 is the successor of 3, etc. All of them are going to be in here. That is axiomatized to be a set in Zermelo-Fraenkel theory, and that's the axiom of infinity that says that that's going to be so. So I've written this out a bit more formally. So the axiom of infinity says that there is going to be this set which we'll call this fancy n, the natural numbers, and it's going to obey these properties that 1, the first element, which we'll just call 0, that's the classic thing to call it, is going to be inside that set, and 2, there's going to be some successor rule that takes elements that are inside here, generates a new element that is going to be allowed within the Zermelo-Fraenkel theory. You know, this thing is allowed. If k is allowed within the Zermelo-Fraenkel theory, then the set containing k is allowed within the Zermelo-Fraenkel theory as something that exists. By the pairing axiom is what we're using there. And this set is going to obey the property that if k is an element of the set, then that has to imply that the successor is also in this set. And so because 0's in there, and this is true, then the successor of 0 has to be in here, and the successor of 0, by what we've just discussed about the successor rule, is going to be something different to 0, it's going to be a new thing, and then because that new thing, which we will call 1, just to give it a new name, a simple name, because that's in here, then again, using this property, the successor of 1 has to be in here, and again, the property of the successor rule means it's something that's new and it's not equal to either of the two things that we've already had, not equal to 0, not equal to 1. So we'll call it 2, and you go on like this, so you end up with all of them. So the axiom of infinity just says that there is going to exist a set like this, and it's allowed within the Zermelo-Fraenkel theory as a set. So we're now going to look at this other construction of the natural numbers, the von Neumann construction. So this previous construction we've talked about here, using this successor rule, this was the Zermelo construction. The von Neumann construction is different. It's going to yield the exact same set up to isomorphism. It is slightly more complicated when you first see it. More complicated to get your head around. The things look, well, not just look, they are more complicated. However, as I've said, there is a massive benefit to this, which is that defining order on the natural numbers comes so easily with the von Neumann construction, whereas it's much more difficult with the Zermelo construction. So how is this going to work? So we're going to start off with the empty set again, which by the empty set axiom is allowed as something in Zermelo-Fraenkel set theory. And the successor rule we're going to use this time to get the next thing along is going to be this, instead of what we had previously. So previously it didn't have this bit, it was just the set containing k, your current thing. Now you want to take the set containing your current thing and union it to your current thing, which of course is going to be a set itself. And that whole set is now going to be the next thing along. So let's work this out for a few of the first few examples. So for the successor of the empty set, it's very simple. So you take the empty set and you union it to the set containing the empty set. Now, by the pairing axiom, the set containing something is allowed as a set itself, and then by the union axiom, you can union that to the original thing as long as this is a set, which it is because we've constructed it thus far in our Zermelo-Fraenkel theory of sets. So you can union those two things together and you'll get up another set. So this thing that you get here is going to be allowed as a set in Zermelo-Fraenkel theory. So take the empty set, union it to the set containing the empty set. Well, the empty set contains nothing, so when you union it to another set, you just end up with that other set back again. So it's just going to be the same as what we had in the Zermelo construction. It's just going to be the set containing the empty set, so it doesn't differ yet. Next, it's going to get more complicated. So the next one along is going to be equal to this. So let me explain how. So we want to take the successor of this. So we're going to take this and union it to the set containing itself. So the set containing itself is now going to have two set brackets there. When you union these two things together, you're going to add their elements. So the element inside this is just the empty set, so that's there. And then you want to union the elements inside here. Well, the elements inside here is just K, so this is K, so it's going to be this inside here. So you're going to end up with the empty set and this set containing the empty set inside overall another set, and that's your next element along. So the next one along really gets complicated, and you can see it's so ugly that it hasn't even fit in the space that it was supposed to fit in, so it's now down here. So let's have a look at this. So we want to take the successor of this thing, so we're going to take this thing and we're going to union it to the set containing the whole thing. So that means we're going to have the two elements that are inside here from this, so we'll have those two elements there, and then we're going to have the whole thing as an element itself. So here the whole thing has come down here, and all of those three things inside a set, that's going to be the next one along. So it's getting uglier and uglier, and you can imagine working out the next one along. Now, we can relabel these up, and relabeling these up actually makes things a lot simpler. So we can relabel these up as follows. So we can relabel the empty set again as 0, and then we'll relabel this element here, this structure here, as 1. And you can actually, let me just point out to you that 1 is then the set containing 0, because 0 is the renamed up version of this. Then moving on, you can rename this whole thing as 2, but again, think about renaming the things inside here. You've got this is 0, this is 1, so 2 is actually the set containing 0 and 1, and this pattern continues. So this thing is going to be relabeled up as 3, but then think of relabeling up the things inside. So 3 is now the set containing 0, 1, 2. In contrast, when you thought of the Zermelo construction, 3 was just equal to the set containing 2, 2 was just equal to the set containing 1, 1 was just the set containing 0. Having all of the elements beneath it, inside it like this, that's why this is going to be so helpful for defining order, so we'll see that later on. So using then the pairing axiom and the union axiom, you can then put all these elements inside a set themselves, and you've then got a finite set containing 4 elements. And you could go on, of course. So you could make the next one along, which is 4, you could make the next one along, which is 5, and put those into a set, a finite set again. What we're interested in is then applying the axiom of infinity to this successor law, and we'll end up then with the same size set as we did with the Zermelo construction, i.e. a set that is isomorphic to the set you got with the Zermelo construction, i.e. we've arrived at the natural numbers in another way. So you can use exactly the same thing as we had here. So 0 again is going to be an element of the natural numbers. So we've got a first structure inside our set. We then have a successor rule that takes each structure that you've created and generates a new structure that is going to be allowed within the Zermelo-Frankel theory. So we've discussed how this, if K is a structure that's being made in the Zermelo-Frankel theory, then this new thing, the successor of K, is still going to be something that's allowed within the Zermelo-Frankel theory. And it's going to all the time yield something new, something that you haven't had previously. It's making something more and more complicated. So it's never going to equal one of the things that you've already had. And then, using the axiom of infinity, we can say that there is a set that exists that has all of them, that obeys this property. That's what the axiom of infinity says. It says that you can now have, using this successor rule and the first element, you can now produce a set that obeys this, that contains all of them. So where if one element is inside it, then the successor has to be inside it too. So you start by putting the first element in, and then you have to have this element in by this, and then you'll have to have this one because that's the successor of this one, and so on. So you'll then have a set containing all of them by the axiom of infinity, and that set will again be countably infinite. You could put this in bijection with this, so it's just another way of constructing this same size set. Remember, in set theory, the symbols of the elements don't matter. The elements themselves might be very different things. You know, these structures are very different to these, but we can relabel those elements up with these same symbols. And as far as set theory is concerned, all that we're interested in is how many elements are in this global set here. That's the only real property of sets, how many elements they have in them, the cardinality. And these two are going to be placeable in bijection with one another and therefore have that same cardinality. They're both countably infinite. So these are two separate constructions of the natural numbers. This one may be simpler, but this one is going to be helpful with defining order properties on this set. So the next thing we want to do in this video is define an order property on the natural numbers and then define the arithmetic properties, the algebraic properties, addition and multiplication on the natural numbers. So let's do ordering first. So ordering is so simple as long as we use the von Neumann construction. So we're going to use the von Neumann construction. So for n1 and n2 are elements of this set that we've now got and we're accepting, and we're using the classical symbols for the natural numbers now. So take two natural numbers and I want to tell you whether this one is less than or equal to this one. So this is a statement that's going to either be true or false. So I need a criteria for this to be true or false, and that's going to be defined, and that's then going to tell me the ordering of all of the elements inside our set. And the way we're going to do this is just using this. It's going to be the case if and only if n1 is a subset of n2. So let's think about this more. So 0 is obviously the element that's smaller than all the other elements. It's the element right at the left on the great big ordering, and it's the empty set. So it's going to be a subset of all of the ones after it. So it's going to be less than or equal to every other natural number, including itself, by the way. So reflexivity is an important property of the order relation, that if you're talking about if n2 is the same thing as n1, that it needs to be true that n1 is less than or equal to n1. And you can see that this criteria is absolutely fine with that, because if n2 is n1, n1 is a subset of itself. So yes, it's true that 0 is going to be less than or equal to every other natural number, including itself. Then if you look at the next one along 1, which needs to be next along in the ordering, so after 0, well, it's clearly going to be less than or equal to 1 itself, because it's contained within itself. This set is contained within itself, so excellent. Its reflexivity is fine, it's less than or equal to itself. But then it needs to be less than or equal to all of these things, and that's fine as well, because, again, think of it simply like this. So 1 is the set containing 0. All of these other ones, they're going to contain 0 inside them. They're going to be sets with 0 as an element. So truly, this is going to be a subset of all of these sets after it. So it's going to be less than or equal to all of the natural numbers after it. In fact, the only natural number it's not going to be a subset of is 0, which is the empty set. So this is not a subset of the empty set. The empty set is a subset of it, but not the other way around. So it's not true that it's less than or equal to 0, which is exactly the way we wanted it to be. So 1's going to be the next thing along in the ordering. 2 then, so it needs to be the next thing along in the ordering. That's what we know we're trying to construct, this classical ordering for the natural numbers. So again, looking at this, it's going to be less than or equal to itself because it is contained within itself. And then it's going to be less than or equal to everything that comes after it, because it's the set containing 0 and 1, and 0 and 1 are going to be in everything after it. So yes, we'll get true is the answer to is 2 less than or equal to all of these, using this rule for working out ordering. And then it needs to not be less than or equal to these two things, and that clearly is true because this is a set that's going to be bigger than this one, because it's got that additional element of 1, which isn't in this set, and it's clearly bigger than the empty set. It's not a subset of the empty set. And you can see that this pattern is going to continue, and it's going to therefore define ordering correctly and encode that information of the classical order for the natural numbers to be in correctly. And it will obey all of those defining properties that an order relation needs to obey. It will obey reflexivity, we've talked about that. It will obey anti-symmetry. Clearly, if n1 and n2 are not the same set and n1 is a subset of n2, then it's not the case that n2 is a subset of n1, so it will be anti-symmetric. And it will be transitive as well, because subsets are transitive. So if n1 is less than or equal to n2 and n2 is less than or equal to n3, then that means that n1 is contained within the subset of n2 and n2 is contained within the subset of n3. So clearly then n1 is contained within n3. So n1 is a subset of n3, so transitivity is going to hold. So it will obey all of the defining properties of an order relation, and indeed this will give the classical ordering that we know and love that should be on the natural numbers. And you can see that the von Neumann construction makes this really easy. Try as a exercise for yourself to come up with a rule using the Zermelo construction. It's much more difficult. That's the advantage of the von Neumann construction. So we've now got the familiar set of natural numbers and we've got the familiar ordering on the natural numbers. The next thing we want to do is define the algebraic properties. We want to define addition and multiplication. So the addition law that we all know and love for the natural numbers obeys the properties of a monoid. It does not quite obey the properties of a group. It falls short because it doesn't have inverses in it, so it obeys the fact that it's closed. It obeys the axiom of having an identity, which is going to be 0. It also is going to obey associativity, but it does not have inverses for elements. Even, for instance, 1 does not have an inverse in the addition of the natural numbers. There's no -1. So it therefore isn't a group, and the name for algebraic structures where they obey those first 3 axioms of group theory but they fall short of inverses is called monoid, and I'm just going to write that down. So we want to make the natural numbers into a monoid with this addition property. So we need to fill in all the rows of this great big composition table, and obviously I haven't written down every natural number, but you'd imagine having this table going on for infinity. So all of the natural numbers up here, all of the natural numbers here, and you need to define what all the entries are going to be in here for what one natural number added to another one is, and it needs to be both ways round. So you need to have what 1 plus 3 is equal to and what 3 plus 1 is equal to. And of course, the familiar addition of the natural numbers is going to be commutative. It's going to be the same no matter which way round you do it. But monoids don't need to necessarily be commutative. It's just that the natural numbers is going to end up commutative. So we're trying to define the classical addition law on here. We're not trying to define something new. So firstly, this first row is really simple. 0 plus every single other natural number. You're just going to give that natural number back again. So 0 plus a is just going to equal a, where a is a general natural number. So 0 plus 0 is going to be 0, 0 plus 1 is going to be 1, 0 plus 2, 2, 0 plus 3, 3, 0 plus 4, 4. So that first line of the table was very easy because we want 0 to be an additive identity. Let's now do the next line of the table, and this is where it gets more interesting. How are we going to define what 1 plus all of these elements is equal to? So we want to work out what all the entries in this row here are going to be. And this, you may think this is going to be really, really easy because of course you know what the answer is, but actually trying to work this out, how you're going to define this, is more complicated than you would think. So we're trying to work out this answer then, 1 plus the general a, where a is varying over all these elements here. The way we're going to do this is using the successor rule, which is why I thought it was so important to introduce that concept of a successor rule earlier on. So we're going to start by saying what is 1 plus 0, which is a simple answer, and then we're going to define everything else in terms of a recursive law where you'll get what 1 plus 1 is from the answer of what 1 plus 0 is, and you'll get the answer as to what 1 plus 2 is from the answer of what 1 plus 1 is. So you'll get each of these answers from the answer of the one before, and then that will then define the entire row here. So let me show you how we'll do this. So 1 plus 0, clearly we're going to define that to be equal to 1 because we want 0 to be the identity, so we want it to take everything to itself no matter which way round you add it to something. So that's easy. We can put in that answer there. In terms of what the answer to 1 plus 1 is going to be, well, we're going to say that it's going to be the successor of the answer to what 1 plus 0 is. So the successor of 1 is 2. Then when you want to know what the answer to 1 plus 2 is, we're going to say that that's the successor of 1 plus 1. So the answer to 1 plus 1 was 2, so the successor of 2 is then 3. 1 plus 3, it will then be the successor of the answer to 1 plus 2, the successor of 3, so it will be 4. That's how we're doing this, and that's how we'll do each of these, because here we'll just have that 2 plus 0 is 2, and then the answer to the next one along will just be the successor of 2, etc., onwards. And the reason that's working is each time you are taking this number and adding it to these, the next thing along, the next answer along in the row is just going to be I know we shouldn't say this because we're trying to define this, but we're just adding 1, so we're just going to the successor along from it, because we haven't changed our number here. All we're changing is this number, and this number's only changing by an amount 1. It's just the successor of it. That's why this is going to work. So let me write down some formulae for this. So in general, this is the rule we're going to use for defining this row. So 1 plus the successor of A, so the thing along from A. So we've defined the first one, we've defined 1 plus 0, so then 1 is going to be the successor of 0. That is going to be, so 1 plus 1 is then going to be the successor of the answer to 1 plus A. So A was 0, remember 1 was the successor of 0. So it's going to be the successor of 1 plus 0, which is this answer. That's the way of writing down what I've told you. So we define the first thing along, and this is the way we're going to do it for all of these rows. We define the first one, i.e. the thing added to 0, which is easy, and then we define everything after using a recursive relationship in terms of successors. So the next one along is just the successor of this. This one is the successor of this. This one is the successor of this, and that's the way you write it, that 1 plus the next thing along, so the successor of A, is equal to the successor of 1 plus A. So taking an example, so 2, if we want to work out what 1 plus 2 is equal to, well, 2 is the successor of 1, so in this case, A is going to be 1, so 1 plus 2 is going to equal the successor of 1 plus 1, so the successor of 2, which is 3. And that's how you're going to define this, so it's a recursive relationship using this successor rule. So let's do the next row along. So we want to define what 2 plus each one of these are. So the way you do it is you start off with defining what 2 plus 0 is equal to. Simple, that's 2. And then everything is just going to be the successor of the one to the left of it. So this is going to be the successor of this, this is going to be the successor of this, this is going to be the successor of this, this is going to be the successor of this. And the way you'd write that is 2 plus the successor of A. So this says if you want to do 2 plus some number, let's say 3, you need to find what was the number before it. So it's equal to 3, so it's the successor of 2. So A, the number before it, is 2. And then you just need to look at what was the answer of 2 plus that number, and then take the successor of that. So 2 plus 2 was 4, the successor of that is 5, so that's the answer to 2 plus 3. So that's how you write it, what we're doing as a formula. So in general then, to define this addition composition table, this is what we need to know, that B plus 0 is going to equal B. That's the answer to all of the first entries in each row, and then to get all of the other answers you just progressively take successors. So for some general B down here, here's the first answer of B. The answer to then what B plus 1 is equal to is it's just the successor of B, and then the next one along is just the successor of that, and so on like that. So this is the general rule, that B plus something, you have to work out what the one before it was, so the one to the left, which is A, and then you just take the successor of whatever the answer to B plus A was equal to, and that's your answer here. And that, you can hopefully see, is going to give rise to the familiar addition table of the natural numbers, which we know obeys the properties of a monoid, of a commutative monoid. So that's addition now defined. Let's move on to defining the second of the two composition laws. Let's define multiplication. And together, the natural numbers with the addition law and the multiplication law on, they're called a semi-ring. So this differs from a ring. Remember, a ring, you need to have a additive commutative group, and then you need to have a multiplicative monoid that obeys the distributive properties. In a semi-ring, all of multiplication still works, everything's the same, distributivity still holds true, but instead of having a commutative group for addition, you have a commutative monoid instead. So clearly the natural numbers is a commutative monoid under addition. So when we put the multiplication on top of that, you don't get a ring, instead you get a semi-ring. So another great big composition table then. So multiplication, we need to define what every natural number multiplied with another natural number is equal to. Now, basic ring theory holds true in semi-ring theory, and by the way, the main example of a semi-ring is the natural numbers. The whole point of defining what is a semi-ring is so that we have a name for the type of algebraic structure that the natural numbers is. Now, in order for distributivity to hold true, right and left distributivity, and indeed it's going to be a commutative semi-ring, so we can just talk about distributivity. In order for that to hold true, 0 multiplied by everything has to give 0. If you don't have that, then distributivity breaks. So we can instantly fill in these parts of our composition table. 0 multiplied by everything is going to give 0, and everything multiplied by 0 is going to give 0. Next, we can fill in the next row down, so 1 multiplied by everything. So remember, we want a multiplicative identity. We know what we're aiming for, remember. We know what these composition tables should look like. We've been using this number system for years. We just want to formally construct it from the ground. But remember, we know what we're trying to build. So we know we want this symbol to be our multiplicative identity. So we're not trying to construct something new. We're just trying to get to what we want. So we're obviously going to then define it this way. So 1 times everything is just going to give that thing back again. So this row is really simple. 1 times 0 is 0, 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4. So nice simple row there. Let's move on to the next one. Next row along then, so 2 times every element. So the first thing here is very simple, equivalently to how the first thing over here was very simple. And indeed, it's very similar to how we did it up here. We're going to use recursive definitions. So all of the things in this column are going to be really simple. So 2 times 1 is just going to be equal to 2, 3 times 1 is going to be equal to 3, 4 times 1 is going to be equal to 4, a times 1 is going to equal a. Next thing along is more complicated. How are we going to get 2 times 2? Well, again, just like before, we're going to define it in terms of the answer to the one to its left. And the way we're going to do it is actually using the addition we've already defined. So 2 times 2 is going to be the answer to what 2 times 1 was equal to, but now you're going to add 2 on. So remember, you've got addition now, it's defined. So you'll add 2. We know that we did a good job up here, so we've got our classical addition rule that we all know and love. So we know what the answer to 2 plus 2 is equal to. It's 4. So that's the answer that's going to be there, which we know is the answer we were aiming for what 2 times 2 is equal to. Then 2 times 3, again, you're going to look at the answer to the left. So what was 2 times 2? It was 4, and you're going to add 2 to it, which is 6. 2 times 4 then, again, you're going to look at what 2 times 3 was equal to, 6, and you're going to add 2 to it to get 8. So each one, you just look to the one to the left and you add 2 to what that is. So let's write down that general formula. So here is that general formula here. So 2 times something is going to be find out what that thing is the successor of, i.e. find out which number or natural number is to the left of it up here, and then take 2 times that, so the answer to the left of the answer that we're trying to work out, and then just add 2 to that. That's all that's saying. So this is the recursive way in which you're going to define all the answers in here. So there are all the answers to that row written in there. Let's now turn to the next row. So again, 3 times 1 is simple, it's equal to 3. And the way we're going to define the other entries here is again recursively. So the answer here is just going to be the answer here, but this time plus 3. So it's not plus 2 anymore, it's plus 3. The next one along, it's just this answer plus 3 again. So writing it out as a general rule, 3 times something, you need to find out what it's the successor of, so the number before it, and then take 3 times that number, so the answer to the left in the table, and then just add 3 to it. And of course you can generalize this. You can see that we can replace 3 with a general b in all of these places. So I've written those entries for the row 3 in there. So the general rule for row b then, you need firstly that b times 1 is going to equal b. That's simple. And then the general rule to work out all the other entries in the row is that b times something is going to be equal to b times the thing before it, so the thing that it's a successor of, and then just add on b to get the next answer along. So that's the general rule for working out the entries in this table, and it's a recursive relation. And hopefully you agree that this is going to give rise to the familiar multiplication composition law that we know and love for the natural numbers. So overall what we now have is this set of natural numbers with the familiar ordering on them, with the familiar addition and the familiar multiplication, and those algebraic properties together are going to be a commutative semi-ring. So what we're now going to do is have a look at the axiom of induction. Now this is going to be my favourite part of the video. I absolutely love logic, and this is about logic. The axiom of induction is a logical axiom. It is an axiom of thought. It's an axiom of reasoning. It is an axiom that says that this is a valid mathematical argument, that proof by induction is a valid mathematical argument. That's what we're going to look at, the axiom that makes proof by induction a valid mathematical argument, and we're going to see why it doesn't just follow from the other axioms of classical logic, predicate logic. So let's do this. So firstly, just before we do that, let me just point out that the successor of k, so where k is a natural number, so the next natural number along, this is just equal to k plus 1 or 1 plus k using that addition law that we've now defined. So before we had the addition law, we had to talk about the successor rule. But we know that we've defined that addition law in the classical way, the way that we know and love for the natural numbers, and that it is true in that perfect addition law that we've used since childhood, that the next natural number along is just that natural number plus 1. So we're going to start, it's no longer talking about the successor of k, well I might still mention it occasionally, but we can talk about k plus 1 instead. So you can see quite clearly here, just looking at this row that's nicely written out, that 1 plus each of these natural numbers takes you to the successor of that natural number. So 1 plus 0 is the successor of 0, 1. 1 plus 1 is the successor of 1, 2. 1 plus 2 is the successor of 2, 3. So when we're talking about proof by induction, we will probably not talk about the successor of k, and instead we'll just replace the successor of k with k plus 1. And I hope you're happy with me doing that now. So proof by induction is all about predicates. Predicates over the natural numbers. So for those of you whose logic might be a little bit rusty, remember in classical logic we deal with propositions and we deal with predicates. Propositions are just thoughts, ideas. You know, the ball is red is a proposition. The laptop is new is a proposition. It is raining is a proposition. The patient is psychotic and needs sectioning. That's a proposition. It's a thought, an idea. Predicates are then generalized forms of propositions. They are a general form that you enter in a variable to get a proposition out. And we use predicates all the time in mathematics, which is why it's such an important concept for us. So this is an example of a predicate. We often write it like this, p of x, to show that it's something that varies with x. You plug in an x and you get a proposition out. So the predicate is the general form where you can put in any one of some sort of variable, and in induction we're talking about varying over the natural numbers, so x is going to be some natural number, and then you'll get a proposition out. So the predicate is the general form. So this, if you like, is the predicate. Now, we can put in examples here. So we could put in x is equal to 0 and ask, is this proposition now true? Is it true that 2 times 0 plus 5 is equal to 1? So in that case, the proposition is false for 0. For 1, if we put 1 into this predicate, we get a proposition. 2 times 1 plus 5 is equal to 1. That's not true as well. So in fact, you can actually see that for all of the natural numbers, this isn't going to hold true. If I change it slightly, just bear with me. So now I've made it 2x plus 5 is equal to 11, and we can see now there is actually a natural number for which this is going to be true. So if you put in x is equal to 3, then that proposition, 2 times 3 plus 5 is equal to 11, that is a true proposition. For all the other natural numbers, when you plug them into this predicate, it's going to be false. It's going to yield a false proposition. So a predicate is a generalized form of a proposition. It's a statement like this where there is a variable and you can put specific entries for that variable in, and then it becomes a proposition that can either be true or false. So it's a generalized form of propositions. Here is another example of a predicate, a general statement where you can put in any of these elements over the set for which this predicate is valid. So here we have the sum from r is equal to 0 to x of r is equal to x over 2 times x plus 1. So it's this summation law, this famous summation law. And this, of course, is true for any of the natural numbers. So if you put in x is equal to 0 here, that's just the sum from 0 to 0. So it's equal to 0. And then when you put in 0 on this side, it's also equal to 0. So it's true for x is equal to 0. For x is equal to 1, this is the sum from 0 to 1. So you'll just have 1 on this side. If you put in 1 here, you get a half times 2, which is 1. And so on. So for all the natural numbers, this statement, this predicate, holds true. So let's state the axiom of induction then, and it is proof by induction. So let's suppose we have some general predicate p of x for x is a natural number. And let's suppose that we know that the predicate is true for x is equal to 0, so we're given p of 0. Let's also suppose that we have this. We have that for all x is an element of the natural numbers, p of x implies p of x plus 1. So if you're given p of x, then you immediately get p of x plus 1 as well. So if this is true, this one is also true. And you know that for all x is an element of the natural numbers, this relationship holds true. Then the axiom of induction says that from those two things, you have this, that for all x is an element of the natural numbers, p of x holds true. So the predicate's going to hold for all the natural numbers if you have those two things. So at first this seems kind of obvious. Why on earth would this need to be a separate axiom of logic? So let's just think about this. So we're given that we have p of 0 and we're given this. So what we can then apply is universal elimination. So for all elimination, and we can say, 0 is an element of the natural numbers, so we can plug 0 into this and we then get p of 0 implies p of 1. So given that we've got p of 0 and we've got this, we can then use implication elimination, modus ponens, from classical logic to say that we've got p of 1. So we've now got p of 0 and p of 1, and then we can use universal elimination again on this statement, say 1 is an element of the natural numbers, so p of 1 gives us p of the successor of 1, and remember we've replaced now the successor of x with x plus 1, so we then get 2, p of 2. So because we've got this and we've got this, again by implication elimination, we've got p of 2, and we can continue on in this manner. We will have p of 2 implies p of 3 by universal elimination, by implication elimination, then we've got p of 2 and p of 2 implies p of 3, so we've got p of 3. So we can continue building on in this way, and we'll have p of 0, p of 1, p of 2, p of 3, p of 4, p of 5, etc, etc, etc. So it seems as though you can get this surely just by the other axioms of classical logic, and indeed let's try doing some universal introduction and arriving at this statement. So we want to produce this then from those two previous things. So to make a statement like this, we need to use the universal introduction rule of inference, and what that says is that you assume x is an element of the natural numbers and you deduce p of x. If you can do that, then you have this by universal introduction. So x is an element of the natural numbers then, and we need to somehow get p of x. Well, it seems as though we're going to be able to do that because of the argument that we've just had. So we know we have p of 0 and we know we have this. So by surely those repeated universal eliminations, we can get to p of x surely, because from p of 0 you can get to p of 1 by universal elimination on this statement using x is equal to 0. from P of 1, you can get to P of 2 by universal elimination on this with x is equal to 1. And onwards, surely, eventually you would be able to get up to P of x. Just do this however many times and you'd get P of x. So surely, therefore, for any x as an element of the natural numbers, you can deduce P of x, and therefore, surely we can have this. So we've just used the other axioms of classical logic to get this. Why do we need a separate axiom to say that this is going to be true? Well, the flaw in this argument is that however many times, just do this process however many times is needed to get to P of x. My question to you is, how do you know that you can do it however many times? And your answer to that is probably, well, that's obvious. You just know that you can do that. It's common sense that you can do that. But when you just know something, that means that you've actually most likely got to an axiom of reasoning, an axiom of common sense reasoning, which is what classical logic is. Classical logic is the study of common sense reasoning, classical reasoning. So that's why this axiom is necessary. That's what it's really capturing, that this is a valid, reasoned argument, that you can do this however many times. This ultimately, that however many times is ultimately what this axiom of induction is capturing. Because how do you know you can do that? None of the other axioms of classical logic say that you can do it however many times. So we do need a separate axiom of logic to say that that is a valid logical argument, and that is what the axiom of induction is. So overall, that is the axiom of induction. It is an axiom of logic. It is about predicates over the natural numbers, and it says that if you are given P of 0 and you are given this thing here, that for all x is an element of the natural numbers, P of x implies P of x plus 1, the successor of x, then you have this. And it is the axiom of reasoning, the axiom of thought, that makes proof by induction a valid mathematical argument. And it is necessary as a separate axiom of logic. You cannot derive it from the other axioms of logic. That's what I just attempted to do here. But that, for however many times it is necessary, is the stumbling block. How do you know you can do that? What axiom of reasoning that's already defined in classical logic says that you can do that? Well, there isn't one. So that's why the axiom of induction is necessary as a separate axiom of thought. So we'll end the video here. I hope you've enjoyed watching that video. I've certainly enjoyed making it, and I hope you've learnt something. Thank you very much.